We'll talk about models. Models are not unique to science, although they are very useful. What I mean by that is a lot of kids, especially boys, built models when they were kids. Model airplanes, model ships, whatever the case may be. And a model is a representation of reality. It's not reality, it's a representation of reality. And we use them in science so that we can test our understanding of the real world. Because the model usually, and particularly in chemistry, represents the microscopic world. We can't actually see it. And I should say submicroscopic. Microscopic world, you can see some things, but the submicroscopic, we're only just now beginning to see bits and pieces of it. And I mean by that, images of atoms and molecules. But the model gives us a representation of those atoms and molecules. And in this case, how the atoms fit together, and in particular, how they bond. So, and models, typically a model will accompany a theory. It's rare to have a model that is fit to a law, because a law doesn't give you enough understanding to construct a representation. So when you hear model, think theory. Let me see, somebody popped in, and
it was me.
Oh, let me scroll down and see. Oh, all right. Let's see. All right. So now I'm only missing Lacey Crow, I think. If I check out the gallery here. Yeah. Okay, so back to models. Whenever you have a theory, you generally have a model associated with it. Not always, but models are very useful. And in most cases, an attempt will be made to model reality in some form or fashion. Now, models don't have to be physical representations, although sometimes they are. A model can be mathematical. In other words, you don't actually have a picture of what the real world is, but you're expressing its behavior in terms of one or more mathematical formulas. Okay, so what are some fundamental properties of models? I already mentioned one. A model does not equal reality. That's first and foremost. Models are simplifications of reality, and as a consequence, very often they're wrong. They may not be totally wrong, but they may be wrong in certain elements of their presentation. So we have to be careful with the use of models. Generally, as models age, they become more complicated, because those things that are wrong we try to fix. Rather than toss it out, we try to make changes. We tweak the model so that it fits reality better. Every model has one or more underlying assumptions, and we have to make those, because if we don't, then there's no way we can produce a useful model. Certain assumptions have to be made, and we have to keep those in mind all the time, because they dictate the ability of the model to work as intended. Now, just because something's wrong doesn't mean it isn't useful. Remember what Edison said about the light bulb. Some reporter, I think it was, he says, how many times did you get that one wrong? He says, I didn't get it wrong. I just found out 99 ways that you can't make a light bulb. I only needed one. So models can also inform us about the real world, even if they're wrong. They just tell us things that don't work, that our assumptions may be wrong, or that conclusions may be wrong. So the models are useful even if they're wrong. Now, what choices do we have if a model turns out to be wrong? Or we might say it stops working. And when I mean stops working, it's unable to predict. When you make a change in a model, you want to see how it responds to predict certain behaviors or conditions or structures, whatever the case may be, in reality. I mean, does the model fit with the data? So if we use a model to do a prediction and it turns out to be wrong, what do we do with it? Well, if it's an old model and it's been working pretty well up to now, sometimes we just restrict its application. We just say, you can use it over here, but you can't use it over here. And that's what we did with classical physics versus relativistic physics. The Newton's physics would be the classical physics. We just say, okay, Newton's physics works if the size, the mass of the particles or the objects are not too small and not too big. Right? If they get really small, like the size of the atom, Newton falls apart. Or if they get really big, like in the neighborhood of a black hole, then Newton doesn't work anymore there either. So in those cases, you need something else. So we just restrict the model's application. Sometimes we can modify the model to accommodate new conditions, and I mentioned that one earlier. And that is very often done. But sometimes, and this is your third option, if the model just completely falls apart, you may choose to throw it out, start all over. And sometimes these work in combination. You restrict one model's application, and then you start working with a different model for the conditions where the old model doesn't work. And you'll have those models operating side by side. Okay. So, bond energies. Whenever you have a bond, we talked about this earlier, it means that the energy level of the molecule or the product is lower than the energy of the unbonded elements. So that means when they come together, they're going to give up some energy. Right? If the energy is lower after than before, then and the energy that was part of the reactants now is free. And what that means also is that once the bonds are made, if you want to break them, you got to add energy back. And that's what we call the bond energy. So it's an endothermic process where you put energy back in to break bonds. Whereas the formation of bond, energy is released, that's exothermic process. Now, what types of bonds can you form? Well, the current models say that, well, actually, not the current model just before the one we're using now, and we won't get to that new model until chapter 9, so you don't have to worry about that one right now. But with the models that we're presenting in this chapter, we have the potential for a single bond between two atoms, like hydrogen. And the bond is represented by two electrons. Two electrons forms one bond, right? So you might have one electron from that hydrogen and one electron from that hydrogen. And in some form or fashion, they end up in this space between the hydrogens, forming a single bond, and we usually represent that with a single dash. So whenever you see a single stroke, a dash, between two atoms, think single bond, two electrons only. Some atoms, some molecules form with two bonds, a double bond. For instance, oxygen. We'll have a double bond between the two oxygens, right? Hydrogen's a diatomic element at standard temperature and pressure. So is oxygen. But hydrogen has a single bond, oxygen has a double bond. What's another diatomic element? Nitrogen. When nitrogen forms, it has a triple bond, which means 6 electrons. 3 strokes, 2 each, 6 electrons. 2 strokes, 4 electrons, 1 stroke, 2 electrons. Now, in general, the strength of the bonding between the elements increases with the number of bonds. It does not increase linearly, though. In other words, this double bond is not twice as strong as that single bond. So if you put a certain amount of energy in to break this bond, it'll take more to break these 2 bonds, but it won't take twice as much. Okay. Similarly, with 3 bonds, this is a very strong bond, but it doesn't take 3 times as much as the hydrogen to break the bond. It takes more than this and more than that, which is why a lot of the nitrogen, all of the nitrogen in our atmosphere is this kind, because it's a very stable bond. And for plants and after we eat it, animals, to use nitrogen for incorporation into proteins and nucleic acids, to name a couple, this bond has to be broken, and different bonds have to be formed between this nitrogen and oxygen, or nitrogen and hydrogen, typically. Then they're available to be used by plants or animals. Now, also, not only does the bond strength increase, but as the strength of the bond increases, the distance between the atoms shrinks. The strength of the bond draws them closer together. So those 2 trends are the qualitative trends, are that strength of the bond increases with the number of bonds, and the length, the bond length, decreases. So the bond strength increases, bond length decreases. And these are examples. So if you take this hydrogen here, let's hold on a sec. Let's do nitrogen. Okay, nitrogen single bond. In some molecules that's possible. It takes 391 kilojoules per mole to break the bond. I know we left the units out here, but it's the relative numbers that matter. Let's find a double bond where nitrogen is bound to another nitrogen here. 607. 418. So 160. Actually, that blows holes in my theory, doesn't it? So a double bonded nitrogen is more than twice as strong as single bond nitrogen. Well, There it is. As a general rule, what I said earlier is true, but there are exceptions. I think the expression is the exception that proves the rule. And the triple bond nitrogen is 900, which, let's see, is it 3 times the single bond? That's a lot more than 3 times. Okay, so nitrogen was a bad choice. But it does show that the bond strength increases with the number of bonds. Okay. Just to reiterate, energy has to be added to the system to break bonds, and that will be a positive sign, right? Endothermic is positive sign. Exothermic to when bonds are formed, energy is released, and that's a negative sign. Exothermic processes. So those things haven't changed in this discussion. So what good is that information? Well, if we have arrived at a value for the strength of a bond in terms of the energy required to break the bond, then we can do calculations for a chemical reaction. And then we can say, or we can predict, that's a better term, we can predict the enthalpy of the reaction if we know the strength of the bonds. What we do is in a balanced equation, we take the number of certain types of bonds that have to be broken, and we multiply them times the energy required to break the bonds. And then when we get the energy back, we subtract that energy. And notice that the bond energy for, let's see, bond energy per mole of bonds, I'm not sure that that's correct, that it should be, yes, okay, so we're taking only the absolute value, right? How much energy do you get back? It may be a positive number, but this negative number here required to, no, this is the positive number. You're breaking the bonds. That's the positive number. Here's the negative number, but you're only taking the absolute value of it. We need to work a problem to show that. So let's look at this one. What's the bond energy? What bonds have to be broken? Well, the problem with this example is that we're not showing you all the bonds. We're using shorthand notation, and that's not fair. So I'll draw it out for you. On the reactant side, we have carbon. That's the CH3 right there. And it's bound to nitrogen. And then nitrogen is bound to carbon. So that's the reactant. Now the product is that, only this time it's bound to carbon. Like that, okay? So the bonds that have to be broken, theoretically, you would break 3 carbon-hydrogen bonds, you would break a carbon-nitrogen single bond, and you would break a nitrogen-carbon triple bond. And then you would subtract from that the amount of energy you get back in breaking these 3 carbon-hydrogen bonds, this carbon-carbon bond, and this carbon-nitrogen bond, which is the same as that one. So really the only bond that changes from here to here is this one, here and here. So we can simplify our work by saying we take this bond energy and subtract those bond energies, you come out with 0. The only one where you get a difference is in these two. So we can take that one and subtract this one and get our answer. So that one, carbon nitrogen, right here, is 305. And then we can subtract carbon carbon, which is 347. And let's see, I went backwards, sorry. And we get minus 42 kilojoules. Okay, so the trick in using this formula is you only use the numbers when you do the calculations in that previous formula right here. You leave the signs out. So it probably would have been better to put absolute value marks around these. That would have been accurate. Okay, and with this value, you can compare that to the actual value for the reaction, which is, in this case, the negative value is exothermic, right? So it's giving up energy in the process. And that tells me that if it's exothermic and it's giving up energy, that the product is more stable than the reactant, because that energy used to be contained over here in the reactant. Okay, so let's get to the theory. We've got some basic tools now. Let's get to the theory. That was operative for at least the first half of the 20th century, was the useful model and the theory and its model for describing how atoms bond with one another. And that's the valence bond theory. Now, your textbook doesn't mention the valence bond theory. They go straight to the model right here. But I wanted to make the connection between models and theories. They do go together. And the localized electron model was derived from the valence bond theory, because the theory had to be fleshed out by Heitler and London, and later improved upon by Linus Pauling, before the model could be validated. Okay, so what does the valence bond theory say? Well, of course, it's a theory, and it has to do with chemical bonds, but the key word here is valence. The only electrons and the orbitals they occupy that interact in a chemical bond are the valence electrons. The core electrons don't enter in this theory. Let's see, did I miss somebody? I heard a...
It was Jeannie. My internet got kicked off.
Oh, okay. That's fine. I was just looking for Lacey. I don't see. No, she's not here. Okay, so that's the theory, that only the valence electrons participate in the bonding. And we're particularly interested in covalent bonding here, because when you talk about ionic bonding, we can pretty much say, all right, for ionic bonding, you've got a cation and anion, they attract one another. End of story. It's not really the end of the story, but it's easier to understand that than it is the covalent bonds. The covalent bonds are believed in this theory to form when an electron in its orbital overlaps with an electron in its neighbor's orbital, and they share that space. And this is just an example where you have, this would be L equals 1, or the P. This is a P-type orbital. Remember the dumbbells? And these dumbbells from these two atoms overlap above and below and give you these bonding regions here, We'll talk about that in particular a little bit more later. But it's just to illustrate the fact that the valence bond theory is very simplistic. It just says these orbitals and their electrons overlap. One electron from one electron from the other, you got a bond. Now, this theory didn't just spring full-blown out of somebody's head. Walter Heitler was a theoretical physicist, and he enlisted the help of a friend of his, Fritz London, to work on the details after Heitler got the bright idea and got the basics started. Then they worked out, actually in one night, they worked out the particulars of using Schrodinger's wave equations, which were the beginning steps of the quantum mechanical model of the theory. So you remember Schrodinger's equations come out with a value of psi. That's a Greek letter psi. And if we square it, that gives us an indication of the electron density around an atom. Well, Heitler took those equations and used them to describe the bond itself, not just the electron density around an atom, but between two atoms that are bonding. And then Linus Pauling came along later and solved a couple of more problems that developed with the model as it was being used by others. It only took him a couple of years to figure it out. So the localized electron model is the way we represent the atoms in three-dimensional space as they overlap these orbitals. And the model itself says that the electrons are still belong to the individual atoms. In other words, if there's one electron from this one and one electron from that one, when they overlap, the electrons, for some odd reason, still remember where they came from. Or the atoms have dibs on one of those electrons, but they're just sharing them long enough to keep that bond intact. So that's what we mean by the localized electron model. We'll work on that a little more as we proceed, and if I don't talk too long. Okay. So there you have the foundation. Electron pairs must be assumed, one of our assumptions, to be localized on a particular atom or in the space between two atoms. So it doesn't smear out over any other regions in the molecule. It's localized either as a lone pair of electrons, it would be localized to one atom, or as a bonding pair, it would be between atoms. So if we have an example, I'll give you an example. Oxygen again. So oxygen has a bond here and a bond there, and then it has a second bond that kind of occupies the space, because when you have a bond between atoms, it's on axis, but any other bonds have to be off axis. So these form like that. Right? So there you have two bonds for oxygen, but oxygen has some lone pairs that aren't being used. Right? So there are your lone pair electrons, and I'm going to show you how to figure that out in a minute with our Lewis diagrams. But these lone pairs are assumed to belong to that oxygen, and these belong to that oxygen, and these in here are shared. So if you've got a double bond, then one electron from one bond goes here, the other there, and the other bond, one goes here, one goes there. So that means that there are only 6 electrons associated with that oxygen and 6 with this one, but it thinks it has an octet because it's sharing in 2 from here over there thinks it's got 8, and the 2 over here in the bond make this one think it has 8. Right? So they think they have noble gas configuration. So those are the 2 types of electrons: lone pairs, bonding pairs, in this localized electron model. Okay, so we're going to describe the valence electron arrangement using Lewis dot structures. Right, that'll come in just a minute. And then we're going to take that information and predict the geometry of the molecule. Remember I said, if you want to know if a molecule is polar or nonpolar, you need 2 pieces of information. Are the bonds polar? Okay. If the bonds are not polar, then you can stop there. The molecule is nonpolar. Well, assuming it has no lone pairs. Okay, that's another caveat. But once you know the polarity of the bonds, then you need to know the geometry. And if you can figure the geometry, then you can say, is the molecule polar or nonpolar? And that's what we do with this model, the Vsepr model. I'll define that later. Part 3 comes in chapter 9, so you don't have to deal with that right now. Okay, the Lewis structure was proposed by G.M. Lewis. He was trying to work out how to describe these covalent bonds, and he had his own theory. Turned out to be not very good, but it was a start. And the one good thing that came out of it was a way of placing valence electrons around the symbol of an atom, so that you could get a representation of what the atom looked like relative to its valence electrons. Right? Because we don't care about the core electrons in this theory. We only carry the valence bond theory. We only care about the valence electrons. So Lewis gave us a way to do that. And it's based upon that central idea that atoms try to attain a noble gas configuration. And a noble gas configuration means that there are, over here, that there are 8 valence electrons in the p orbital. Now it works pretty well, like I said yesterday, for the 2nd and the 3rd period. It gets a little muddy down here because you're introducing the effects of the d orbitals. So we'll talk about that. That's one of the things that makes the theory kind of hard to deal with. It's when you get into the d orbitals. But this is where we're starting. All right. Everybody wants an octet except hydrogen. Hydrogen follows the Duet Rule. And the Duet Rule just means that hydrogen is happy when it has 2 electrons. Whether they belong to each hydrogen or whether they're part of the bond, it wants 2, so it can look like helium. And it wants that noble gas configuration. Everybody else follows the octet. Right? Like fluorine wants to look like neon. Right? Fluorine only needs 1 more electron to complete its octet. Right? That's true for all of the halogens. Right? I'm pointing at my chart. All of the halogens only need 1 electron to look like their next door neighbor. Noble gas. And there's the representation of our covalent bond. Here's double bonds, right, between the carbon and the oxygen on this side and the carbon and the oxygen on that side. So what does that tell you? Well, it tells you that carbon probably likes to have 4 bonds if it can have them. Doesn't always have them, right? It might have lone pairs somewhere. But this is the only way that carbon can form its octet, because where is carbon located? Carbon's located right here. right? It needs 1, 2, 3, 4 electrons to look like neon. So it gets one of those electrons from each of those bonds, single and double bonds. That means 4 bonds, 4 electrons added to its already 4 electrons makes it look like it has 8. So carbon's happy. Oxygen needs 2 each. So this oxygen is taking 2 from here, 1 from here, and 1 from here, extra, which makes it feel like it's also neon. And same for that oxygen. Nitrogen has 5 valence electrons before it bonds, so it needs 3 more. So this nitrogen gets 1, 2, 3, 1 from each bond. And it looks like, it feels like it's neon. Okay, how do we write a Lewis structure? These are the rules just written out, and we're going to actually do one because that makes more sense when you can see it done. But you start with the number of valence electrons for all of the atoms, and which means you need a formula. You need to know the formula of your molecule first. Then you take all of those electrons that you've added up, the valence electrons from all the atoms, and you stick them together. Now, if it's a small molecule, it's very simple. You just put the more electronegative atom in the center. If it's a complicated molecule, lots of atoms, then you might need some help getting things arranged properly. And I'm not going to throw any bad ones like that at you, so don't worry about that. And you try to give the atoms a noble gas configuration. And I'll show you how that works, except for hydrogen, of course, it's Duet Rule versus the Octet Rule. So here's an example. Say we have water. Oxygen is the more electronegative atom, so it's in the center. And hydrogens are attached to the oxygen, not to each other. In fact, hydrogen can only have 1 bond because it only has 1 electron. So you couldn't bond hydrogen to hydrogen and still have a place for another atom. It won't work. So for other reasons, you have to have oxygen and hydrogens bound only. So add them up. How many valence electrons does hydrogen have? It only has 1 electron, so that one's easy. So both of them together means 2. 2 electrons for the hydrogens. How many does oxygen have? Well, oxygen is in the second period, and it's 6 steps over from the left, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen. 6 valence electrons. 6 plus 2 is 8, so we have 8 electrons to work with. Now what do? You form a single bond between oxygen and the hydrogens, right? And then you subtract those number of electrons from your total, right? How many did we have? 8. So we have 2 on this side, 2 on that side is 4, from 8 is 4. We have 4 electrons left over, right? Where are you going to put them? You can't put any more on hydrogen, and you can't form any more bonds because hydrogen doesn't have any more electrons to work with. So the extra electrons have to go on oxygen, right? Those are the leftover. Those are the leftover. And why didn't we put them here? Oh, here they go. Sorry. So our extra 4 electrons go on the oxygen, lone pairs, right? There's a pair, there's a pair. And then you can satisfy yourself, do we have all of our electrons counted for? There's 2, 4, 6, 8. They're all covered. Now that's the basic Lewis dot structure right there. We're not saying anything about the geometry yet. Right? We know that's not the right geometry. But I won't be able to explain that to you right now. So let's just concentrate on Lewis dot structures. Okay, here's PBr3. How did we arrive at that? Not going to tell us? Okay, let me back up. Let's do PBr3. Phosphorus tribromide. Okay, where's phosphorus? It's right under nitrogen, which means it has the same number of valence electrons because it's in the same group. That's 5. There's 5 electrons. Count from the left. Right? Count from the left. 1, 2, 3, 4, 5. So we have 5 valence electrons here. Bromine, how many does it have? Well, it only needs 1 more to make 8, so that means each one has 7. All the halogens have 7 valence electrons. So 7 times 3 is 21, plus 5 is 26. So we have 26 electrons to work with. Phosphorus is not the most electronegative in this group, I don't think. Well, it could be because it's above bromine. They might be equal. But when in doubt, take the formula. Right? You're not going to be able to bind a bunch of bromines to each other. So phosphorus is the logical one. It goes in the middle. So there are your 3 bromines, and you form 1 bond each. Okay, so that's 2, 4, 6. You have 20 electrons left over. Now, what do you do with those 20 electrons? Well, you start working from the outside inward. Start placing them. 20 electrons. So we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18. Now, why did I stop there? I stopped with 18 because I can't put any more around bromine. It already has 8, right? 2, 4, 6, 8. Right, 2 from the bond. So it's 8, 8, 8. But we still have 2 electrons. Where do they go? Well, they go on the central atom now. Like that. And that's used up all of our electrons. So now we have octet, 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 2, 4, 6, 8, octet. Okay, this one worked out well. Okay, you can do the same thing with HCN. Probably ought to do it. Let's do hydrogen cyanide. Because hydrogen cyanide is going to force us to create bonds. We didn't have to create bonds with phosphorus tribromide, but in order to complete the octets, we will have to create some more bonds. So let's see how that works. HCN. Okay, so how many electrons? 1 here. Carbon's 4 from the left, so it has 4. Nitrogen is 5 from the left, it has 5. So that means we have 10 electrons. Okay, carbon's in the center. Nitrogen, hydrogen. So 2, 4 gives us 6 electrons. Now, where are we going to put the 6 electrons? Start from the outside, work in. Hydrogen's got all it can handle. Can't hold anymore. So can we put all 6 of them on nitrogen? Yeah, I think so. 2, 4, 6. There we go. So we got 2, 4, 6, 8, 10. Used up all our electrons. Problem is, we haven't created octets for everybody. And if you can, you should. Now, nitrogen has an octet, hydrogen has a duet, but carbon is short, right? 2, 4. It needs 4 more electrons. So what do? We take these 2 and these 2 and form 2 more bonds, right? So if we erase these and put them in here, right? 2 electrons, 2 electrons. Now we still have 2, 4, 6, 8 for nitrogen, 2, 4, 6, 8 for carbon, and 2 for hydrogen. So that is a valid Lewis dot structure with a triple bond between the carbon and nitrogen and a lone pair on the nitrogen and a single bond between carbon and hydrogen. That's a representation of hydrogen cyanide. Okay, so we're not going to spend as much time on the others unless there's a point to be made. Okay, this just says that those 2 lone pair electrons probably reside on this side and the hydrogens on this side, which makes it bent. But we'll say more about that later. How about Lewis dot structures for these? Well, we'll have to, I'm running out of time, so I'm going to have to skip those. Work on those problems. In your review document, you'll have several examples there. And just use the rules that I'd illustrated to you here. And with some exceptions, and I'll show you those exceptions in just a minute. So sometimes we don't have enough electrons available to make an octet. And in that case, there's nothing we can do about it. See, in this case, boron is 3 positions over from the left in the second period. So it has 3 valence electrons. And then each hydrogen has 1. So that's 3 plus 3 is 6. We make bonds, 2, 4, 6. We're out of electrons. There are no more left. We know this compound exists. It's isolated and characterized. So we just have to say, this boron is octet deficient. There are not enough electrons to make an octet. But it's obviously stable enough with only 6 electrons. Maybe it figures that's as good as it's going to do, because it started off with 3 valence electrons. Now it has 6. Oh boy, I'm making progress. Couldn't make it all the way to octet, but you know, sextet is okay. And then there's some that have more electrons than they need, right? Like this one, Sulfur Tetrafluoride, has 34 electrons. We form the bonds, we fill the octets, we got an extra pair left over. It has to go on the sulfur. So the sulfur exceeds the octet. 2, 4, 6, 8, 10. 10 electrons. Or you might have to form those bonds without the lone pairs. 2, 4, 6, 8, 10 around arsenic in order to make to use up all 40 electrons. Now, why does that work? I mean, we know these compounds exist. They're isolated, characterized, they're real. So we have to explain why they're there. Well, the localized electron model doesn't necessarily explain it very well, not even with Lewis diagrams. But we can rationalize the existence of these excess octets, because where is sulfur and where is arsenic in the periodic table? right? There's arsenic right there. It's in the fourth period. So what does the fourth period have access to? What does n equals 4 have access to? Right? You have L, you have 4 L's. 0, 1, 2, 3. 0 is S, 1 is P, 2 is D. So we have access to d orbitals in both of these examples. Sulfur and arsenic both have access to d orbitals, and they use them to accommodate those extra electrons. Okay, Lewis dot structures for these guys. There they are. And I can't, this one exceeds the octet, that one exceeds the octet. This one's a perfect octet for boron now. Okay. The second row elements never exceed the octet because they don't have access to d orbitals. Third row and heavier elements often exceed the octets because they have access to those higher level orbitals, the d orbitals. That's just reiterating what I said. If you've got extra electrons, you have to put them someplace. You can't just leave them out. Now, what do we do with ions? Right? This nitrogen, this nitrate ion, right, which may be bound with sodium nitrate, could be potassium nitrate, it could be nitric acid. Stick a hydrogen out here. But the nitrate ion itself, we can treat it with Lewis structures. And if we do that, we have 24 electrons, and we put the electrons around here. But why do we have 24? Nitrogen has 5. 3 oxygen is 18, is 23 electrons. You've got a charge. That's an electron. So we have 24 electrons for this ion. Don't forget the ions. And then we build our Lewis dot structure. And all of these oxygens are equivalent. So that's why you can have, this one is a valid structure, that one's a valid structure, that one's a valid structure. They're all 3 valid. And we put the negative charge out here in outside the bracket because that negative charge is assigned to the entire ion. This is a polyatomic ion, so the charge is not localized. Even though the model says localized electron, the charge is not localized for this group. So we have to put it outside. But the electrons responsible for it are on the inside and part of the molecule. Now, why do we write it that way? Well, that was one of the problems with using the Lewis dot structure. You could come up with more than one valid Lewis dot structure. And then what do? The model itself doesn't allow for drawing things like this. I'm going to leave out the extra dots just to illustrate. That sort of half double bond or partial double bond means that all of these bonds are equal. And that's proven. Experimental data says that all these bonds are the same strength, the same length. But the Lewis model, the way we draw them, doesn't allow for that. Because then you don't know where to put the electrons, because how do you assign electron numbers with a dashed bond? It doesn't exist. So Linus Pauling came up with this idea. He said, we're introducing a concept I call resonance. The molecule flips back and forth among these three? Actually, it'd be better if we put it in like a circle with arrows going all different ways, because it might go from this one to that one instead of going to that one. But be that as it may, this is a resonance structure, and we have to draw it this way. So now we've got the model, the original model, and now we've got to tweak it. And resonance is one of those tweaks for the model. We can still use these individuals when we expose them to some other chemical and induce a reaction. Then this still helps us understand how the reaction proceeds. But just standing alone, we have to draw them this way to account for the equivalence of these Lewis dot structures. Okay. I'm not going to have time to finish that one. Let's say we have a valid Lewis dot structure, and then we can draw another one, but it's radically different. It doesn't lend itself to resonance, but it's a valid structure. How do we know which one is useful? In fact, for resonance structures, each one of these is equivalent in terms of this new concept I'm going to give you, formal charge. The formal charge is a way of bookkeeping electrons, kind of like the oxidation state that we used earlier. The formal charge is more useful for covalently bonded compounds. What it says is the formal charge, which is not really a charge, it's just a way of expressing it. Formal means we perspective, write it down. You take the difference of the number of valence electrons on the free atom before it bonds, and then the number of valence electrons assigned to the atom in the molecule. Subtract that from the free atom valence electrons and see what you get. Okay? If you have more electrons in the molecule than you do in the free atom, then you come up with a negative valence charge, formal charge for the atom. If there are more free atom electrons than you have in the molecule, then you come up with a positive formal charge. And the reason we do that is because the theory, the idea is that Lewis dot structures are best representations when we tend toward zero. In other words, no difference between the free atom and the bound atom in terms of the number of valence electrons. Sometimes you get zeros all around, sometimes you don't. But if you get two Lewis dot structures, and one of them has like -2, -3, -4, and the other one has -1 or 0, you're going to pick the one with 0 or -1. That's what that says. Okay, this is just a formula. How do you tell the valence electrons that are assigned to an atom in a compound? Well, you take the number of lone pairs. Let's take water. We drew it like that before, right? So how many electrons do we assign to each one of those in the molecule? Well, if the electron is coming from a bond, then the atom only has dibs on one of them. Like there are 2 of them there, so it only gets 1. So we have 1 and 1 here. How many do we have here? We have 1, 2, 3, 4, 5, 6. Those are the assigned electrons in the molecule. Now, how many valences do we have in the free atoms? Well, hydrogen only has 1, right? So the The free number is 1 and 1. How about oxygen? Oxygen is 6 members over, so it only has 6. Right? Subtract the assigned from the free. 0, 0, 0. Right? That's ideal. A 0 formal charge on each of those elements in the water molecule. Okay, so these are just reminders, the rules for determining formal charge. If we took this example, we would find that phosphorus has 5 to start with as a free atom, but now it only has 4. 1, 2, 3, 4 right there. So its formal charge is +1. Those are your valence electrons in the free atom. Those are the assigned electrons in the molecule, formal charge 1. Do the same thing for oxygen. 6 in the free atom. Now it has 7, right? 2, 4, 6, 1 here is 7. So it has a -1 formal charge. Chlorine is 2, 4, 6, 7. It only gets dibs on half of a bond. So 7 minus 7 is 0. So the formal charge on phosphorus is +1, oxygen -1. All the chlorines are the same, 0. And that's not bad. That does tend to minimize the formal charges. Another rule, if the molecule is neutral, then all of the formal charges have to add up to 0. And no problem here. 0 plus 0 plus 0 is 0. But the previous one, right? +1, -1, and 0, that's 0. If there's a charge, like with our nitrate ion, then you add up all the formal charges, they have to equal -1 for that molecule. Okay, so we still have to keep that balance. The formal charges must add up to the charge on the group. And here's an example of non-equivalent Lewis structures, right? This is carbon dioxide that we understand it to be. This is a valid Lewis structure, but it's not the same as the other one. And if we do the formal charges, we find out that the formal charges are lower on average for this model or this representation than for the other one. Just a reminder, formal charges are not real charges. They're just a bookkeeping method. And actually a bigger warning about Lewis structures is that these formal charge ideas can lead to erroneous predictions. In other words, no matter what we decide on paper, whatever that decision entails, whatever that decision says for the behavior of the molecule has to match the real world. In other words, if we make measurements on that molecule in the laboratory and we make predictions from our theory, the theory better match reality, or the theory gets what? Restricted, modified, or thrown out. One of those. Okay, I'm about out of time, but I got to finish this. So, as usual, you guys are free to depart if you have to, and I'll finish up the lecture so that we'll be able to look at the next Tuesday. Look at the review document. But I want to get this done, and I'll post it in the video. If you can stay around, fine. If you have to go, then I understand. Okay, so now that we have the Lewis dot structure, how can we use that to give us information about the geometry of the molecule? We use this model, which is part of the localized electron actually it's part of the valence electron theory, the valence bond theory, excuse me. It's runs parallel with the localized electron model and uses Lewis dot structures to determine the geometry of the molecule. And it's really pretty good at predicting geometries. The Vsepr model, what does that stand for? Valence shell. In other words, those electrons in the valence shell, electron pairs, and they repel one another. Even if the electrons are in a bond, we say that they repel one another. Bonds repel. Now, I'll say one thing here. Somebody was playing fast and loose with the concept in order to name this Vsepr. Valence shell electron pair repulsion may be true in one respect, but when we start bookkeeping and making deductions about the structures of molecules, it's not electron pairs, it's electron groups. And that'll become obvious in just a minute. Okay, so the localized electron model does predict the bonding around an atom in a molecule, but it doesn't say anything about the structure. So we use the Vsepr to predict the geometry of the molecule around a central atom. Now that central atom, if it's a simple molecule, that's the only geometry for the molecule. Right? If it's only got one central atom. If it's a big molecule, it may have several centers here and there, and then we have to describe a molecule with multiple geometries throughout the molecule. It might be linear over here, and it might be tetrahedral over here. It might be bent at one place. So the Vsepr is focused on a central atom. And we're going to start off with the simple ones first. You know, I'm not going to hit you with, I don't know, a huge amino acid or something like that, or a polymer. So what the central idea here is to minimize electron group repulsions. So what does that mean? That means the electron pairs for individual bonds, or groups for doubles and triple bonds, they repel one another, right? And you try to position them so that their repulsion forces are minimized. That means as far away from their neighbors as possible. That's the central idea for the Vsepr model. Okay. So we're going to have three-dimensional arrangements of atoms in molecules. And this is where it takes a lot of practice to get the feel for this. And in this method of lecture, we would be better to have models in hand, right? Have molecular models that we could build and see how they are arranged. It's useful here, but if you take organic chemistry, it's going to be absolutely essential. You won't get through organic without a model set. So just a word of warning. So what types of structures can we produce? Well, we could have a linear model, right? All the atoms line up like that, 180-degree bond angle. Right? For example, carbon dioxide, right? Notice it only has 2 electron groups and no lone pairs. So that's a linear model. Just an example. Trigonal planar. We looked at a trigonal planar earlier. Like that. The bond angle there is 120 degrees. Right? You have to think about your days in math class, geometry. You know, what do these angles have to add up to? Well, if they go all the way around the center, they have to add up to 360, don't they? 120, 120, 120. 180, 180, 360. Tetrahedral, that was a little more difficult to deal with. So if you have a tetrahedral, I'll give you an example. You need 4 atoms attached to the central atom. Notice that chlorine is a dotted line. It's in the back. Right? So they form a triangle down here, and then the apex forms kind of a triangle. That's a tetrahedron, which is a triangular-based pyramid. And all of these chlorines in this carbon tetrachloride are spaced evenly about the carbon atom with a bond angle of 109.5 degrees. Okay? That's as far apart as they can get. There are others, and we'll look at those in a minute. So, how do you use the Vsepr model? First, you have to draw the Lewis dot structure. So you got to get good at that. Then you count the electron pairs, actually groups, and arrange them in a way that minimizes repulsion. Put them as far apart from one another as possible. Now, remember, there can be 2 types of electrons around the central atom, the bonding pairs and the lone pairs. So at this stage, you're counting everybody, lone pairs and bonding pairs, or bonding groups, actually. And then you take that number around the central atom and you apply it to the geometries that give you the least repulsive forces among those electrons. Now, once you've decided how the electrons, if there are any lone pairs in there, how they're arranged, the electronic geometry, then you cover up the lone pairs, and the atoms themselves that are bound tell you the molecular geometry. Sometimes they're the same, right? If you don't have any lone pairs, then the electronic geometry is the molecular geometry. But if you have lone pairs, then you might have a different, well, you will have a different molecular geometry to the electronic geometry. So here's an example. So we drew hydrogen cyanide a little earlier, and it didn't have any lone pairs. It only had 2 groups. It had a triple bond group on this side and a single bond group on that side. You treat them equivalently, right? So that's the first assumption, that they're equal. And we know they're not. But for the model, you've got 1 on this side and 1 on that side. That means the farthest apart they can get is 180 degrees. That molecule is linear, both electronic and molecular. How about pH 3? Well, pH 3 is a trigonal pyramid. Why is that? It's a trigonal pyramid because it has a lone pair on the phosphorus. So we have 1, 2, 3, 4. 4 electron groups means tetrahedral. So the bond angle should be close to 109.5. But if you cover this one up, what does that leave you? Well, you're going to have a lone pair up here, phosphorus in the middle. Then you're going to have a hydrogen here, a hydrogen here, a hydrogen here. So there's your tetrahedron. But if you cover up the lone pair, what do you have? These things don't move, right? So what does it look like? Well, you have a trigonal base with phosphorus at the apex. That's a trigonal pyramid. Now, the bond angles are not 109.5. Why? The reason is, if there were another hydrogen up here, yes, because the electron distribution would be equal all around. But with a lone pair, what is a lone pair? What a bond tends to do to a pair of electrons is constrain it between or near the atoms that are bonding. But if it's a lone pair, it's got nothing on the other side holding it down. So it tends to balloon. And when it balloons, it puts electrostatic pressure on these bonding pairs, and it makes them move down. So the bond angle shrinks from 109.5 to 107. Okay? Sulfur tetrafluoride. In this case, sulfur has 2 lone pairs around it. So 2 lone pairs and 4 fluorines gives you 6 groups arranged. And 6 groups means octahedron. We'll look at that in detail in just a minute. Here we have ozone, O3. It has some lone pairs, right? So we've got a bent molecule. Krypton tetrafluoride. We just said noble gases don't like to play with each other, but when we force them, we can make a molecule out of krypton and fluorine. It's square planar. All right, we're going to look at how we arrived at those things in just a minute. The Lewis dot structure for carbon dioxide, I drew that before. No lone pairs. Does it have polar bonds? Yes. Oxygen is more polar than carbon. It's to the right of carbon. So the polar bond says in that molecule is like that. Right? But there are no lone pairs. So the bond angle is 180 degrees. That means that these polar bonds cancel one another out. That means carbon dioxide is nonpolar. Now, lone pairs. If we have lone pair electrons, that tends to put a very large negative charge on one side of the molecule, doesn't it? So the question is, if you have lone pairs in a molecule, does that automatically make it polar? If you only have one lone pair, probably does. But if you have 2 lone pairs, not necessarily, because they try to get as far away from each other as possible. And if they can, 180 degrees from one another, then they cancel one another out. But if they can't, like water, like that, then you have a tetrahedron electronic structure, but you have a bent molecule. Molecular structure. Now the bonds are going to be polar this way, but the electron pairs are also in the back, up and in the back, and they tend to make it more negative on that side too. So this molecule is going to be more polar than you would expect from just the bonds, because you have both of those electron pairs on the same side of the molecule. They really have no other place to go. If you put them over here and put the hydrogen over there, they'd still be the same distance apart. So those lone pairs add to the polarity of the molecule, but they don't. To answer this question, just because you have lone pairs, you don't necessarily have a polar molecule. You can have, and they can make the molecule more polar, but it depends on the geometry. And in that case, the electronic geometry determines whether the molecule is polar. Got a gnat bothering me. Okay. So let me see where we are. If I can take time. We're getting close. Let's do this one. Wait a minute. Let's save this one until we describe. I want to describe the geometries, right? I'm throwing out these terms like linear, trigonal, planar, tetrahedral, like you understand what I'm talking about. So let's skip this slide and go to the geometries. And if you have the number of electron, they say electron pairs, I say electron groups. The number of groups is 2, then the arrangement of the electron groups is linear. That's as far apart as they can get. Now, if they happen to be part of a bond, like this one, this molecule, which is probably carbon dioxide, then the molecule will be linear also. What if there are 3? If there are 3 groups, then trigonal planar puts them as far apart as possible. And there's another example. This is probably boron. I don't know what it is. But it's trigonal planar if, and it's all in the same plane, but they're arranged in a triangle. If you have 4, then the tendency is toward tetrahedral structure. What if you have 5? Well, 5, the best arrangement for the electron groups is trigonal in this plane, but with an apex here and an apex here, opposite one another. So that's trigonal bipyramidal. So you have a trigonal base with a pyramid on top and a pyramid on the bottom. Okay, that puts everything far apart. And the bond angles, if these are all atoms, the bond angle would be 90 degrees for these two, 120 degrees for these two, and they left one out, didn't they? 180 degrees between those two. Right? So it's 90, 120, 180 are all the bond angles. If you have 6 electron groups, then the arrangement is octahedral. Now, why do we say octahedral? Octa means 8, and hedral means surfaces. So we have 8 surfaces. Well, if you look at this, this might be hard to see, but there's one there, there's one in the back, there's one on the right, and there's one in front. That's 4. And you got a mirror of that on the bottom, so that's 8 surfaces. That's the description of the nearest geometric shape that resembles what we have. That's not actually the molecule, because the molecule is made up of a central atom and lone pairs and bonding pairs. Right? So any angles that you think are associated with the octahedron from your days in geometry are not the angles that we're interested in. We're interested in what's the angle with the central atom at the vertex of the angle, and then the other bonded atoms form the, I forget my terminology now, but the angle is with those 3. So 90 degrees here and 90 degrees here. So the octahedron, the bond angles are all 90 degrees. Now these are ideal. If all of the atoms bound at these positions are equivalent, then you will have 90-degree bond angle. If you have a lone pair, or if you have an atom with a different electronegativity here, then the bond angle might change a little bit. But this is our starting point. And octahedral is as high as I'm going to go for electronic structure. They can go higher, but we're not going to go there. Now, if we have 4 groups, electron groups, and form the tetrahedron, and each one of those groups is attached to an atom, then the molecular structure is the same as the electronic structure, a tetrahedron. Our earlier example where we have one lone pair up here, and I think phosphorus down here, then when you cover up this one, what do you have left? You have a trigonal pyramid right there. If we have 2 missing, then we only have this bent molecule, or V-shaped. I like bent. But some books say V-shaped. Some of them say angular, which could be almost anything. I like bent. That's our water molecule. That's an example there. Okay, what if we have 5? Right, we have 5. 1, 2, 3, 4, 5, and they're all occupied with an atom. Well, now you have a trigonal bipyramidal molecule as well. Now it gets tricky when we make one of those a lone pair. Where does the lone pair reside? Well, the lone pair resides, is preferred in a position that minimizes its repulsive effect more so than the bonded electrons. Why? Because this thing tends to balloon, right? It's not bonded to anything, so it balloons out here and it needs more space. So we put it in a position where its bond angle, at least between these, is 90 degrees, and between these would be 120. If we put it over here, then it would be 90 degrees for everybody. It wouldn't give any extra room. So that's why we put the lone pair out here. If there's one lone pair in that molecule. So then what does it look like? Well, it's kind of on its, if you turn it on its side, anybody who's ever played with a seesaw, I don't know if they put them on playgrounds anymore, but the seesaw, this will be the base of the seesaw here, and this will be the board across the fulcrum, where one person sits here and one person sits here, and you rock it. So that's why they call it seesaw. It looks like a seesaw if you turn it on its side. Now, what if 2 are missing? Well, still we put those 2 in this position because it gives them more room. And if we then look at the molecule, after we cover up the lone pairs, we have this T-shape. That's what you have with a trigonal bipyramidal electronic structure with 2 lone pairs. You have a T-shape. Now, if you have 3 lone pairs, then this is the most logical place to put them. And you end up with linear. You know, it just occurred to me, this T-shaped molecule, wouldn't it be better if we put the lone pairs at the upper and lower apex? That puts the lone pairs way away from each other, 180 degrees, and 90 degrees from the bonding pairs. Let's see, would that make it better or worse? Well, the only way to answer that question is with experimental data. The experimental data will tell you whether or not you have a T-shape or a trigonal planar. And I think you have examples of both. Okay, it may also depend on the size of the atoms, right? Because they're going to take up space too. And I'll just leave it at that. Okay, let's see. Yeah, I'm gonna leave that other one behind and just continue on with these guys, because this is a good example of what happens when you take a molecule that's neutral and then you do something to charge it, put a charge on it. What happens to the structure, right? So with phosphorus pentachloride, we will draw the Lewis dot structure. There. And we'll count up the electrons. So phosphorus is 5 and chlorine is 7 each, so that's 35 and 5 is 40. 40 electrons. And now we put phosphorus in the middle. With 5 chlorines. Okay, 2, 4, 6, 8, 10. 30 electrons left, right? How many more do we need on each chlorine to make an octet? Well, we've got 1, so we need 6 more, right? 2, 4, 6. Each chlorine is going to be the same. So 6, 1, 2, 3, 4, 5 times 6 is 30. Use them all up. Okay, so now count up the groups. 1, 2, 3, 4, 5 groups around the central atom, which means what? Trigonal Bipyramidal. So you have a triangle here with phosphorus in the middle, and we have a chlorine at the apex of each, at the corner of each, and then we also have a chlorine up here, chlorine down here. That would be your shape. They're no lone pairs, so the electronic and the molecular are the same. Trigonal Bipyramidal. Okay, what about PCl4 plus? Okay, we still have 5. We have 4 times 7 is 28. But we're missing 1. So that should be 27. Or from the total, let's say 5 would be 33 minus 1 is 32. 32 electrons. So now we put phosphorus in the middle. We have 4 chlorines. All right, so that's 2, 4, 6, 8. 24. So now we need 6 here, right? To make an octet. So 1, 2, 3, 4 times 6 is 24. So each one of these gets a full octet. Right? So with 4 groups, what's the shape? Well, electronic and molecular in this case, because they're no lone pairs, is tetrahedral. Right, so this is tetrahedral. Okay, simply by removing 1 chlorine and giving it a plus charge, we form a tetrahedral molecule. Let's see. Oh, we've got slides to go with that. Here we go, trigonal bipyramidal for the first one. For the second one, see if I got my count right, 32 electrons, that's true. Oh. Right? Have to have the charge. If you don't have the charge, then that doesn't look right. Right? You would expect it to have another electron in there somewhere. And that's tetrahedral. Okay, how about the one where you have an extra chlorine and negative? I'm not going to draw this one because I've got it here on the slide. So with this one, you have 48 valence electrons. We had 47 and one charge, so that's 48. And you have 6 chlorines positioned around the molecule and no lone pairs. So 6 groups means octahedral with a negative charge. Okay? Okay. This just mentions the fact that for many years, it was believed that compounds with the noble gases were forbidden. They were impossible. But that just goes to show you that you never tell a scientist that something's impossible. He or she is going to find a way, if at all possible, to defy that prediction. And they did. They formed compounds with krypton, xenon, and radon. And notice where those compounds come from. I mean, where those noble gases come from, right? Krypton is way down here. Xenon, radon, right? The bigger ones are the ones that tend to form compounds. It's more difficult and virtually impossible to form a compound with argon, neon, and certainly not helium. Okay, so here's an example. Xenon Tetrafluoride. So let's predict its structure. Xenon. How many valence electrons in xenon? 8. It has a complete octet. 7 each for fluorine, which is 7 times 4 is 28. Which means we have 36 electrons. Okay, so we put xenon in the middle. Fluorine's around. Okay, 2, 4, 6, 8. 2, 4, 6, 8. Xenon. 2, 4, 6, 8 means 28. So 2, 4, 6 on each one. 1, 2, 3, 4 times 6 is 24. So we have 4 electrons left over. They have to go on the xenon. So xenon has exceeded its octet. But what's the electronic structure? 1, 2, 3, 4, 5, 6 octahedral. Okay? What does that mean? Where do we put the lone pairs? Well, in an octahedron, you have 90-degree angles all around, except for the apexes. That's 180 degrees. That's as far apart as you can get those electron pairs, is to put them at the apexes. Right? They're far enough away from the chemical bonds, and they're far enough away from each other. So what does that mean? Well, if we put one up here, like let's lay it flat. Xenon in the middle, then we put a lone pair up here and a lone pair down here. That's your octahedron electronic structure. But how about the molecular structure? It's square planar. All of these fluorines are in a plane, same plane, and they're on a square. Okay. So, maybe some final words. Let's see. We're coming down the home stretch. Let's see. This is just a restatement. The arrangement of the lone pairs and the bonding pairs determines the molecular structure. Now, these are possibilities for xenon tetrafluoride. If we go with this arrangement where the lone pairs are in the square plane, then we would get a seesaw. The problem with that is that they're too close together. Now, seesaw was one of the predictions earlier described, but the other possibility is the square planar, where the lone pairs are opposite at the apexes. Now, how do we break the tie? How do we say this is valid, that's valid, which one wins? You look at the polarity of the molecule. If the seesaw is correct, then you're going to have a net dipole in one direction or the other, either this way or that way, depending on, probably toward the lone pair electrons, even though the fluorines are more electronegative than xenon. I would predict that the dipole would be toward the lone pairs. But be that as it may, the difference between the two is one's polar and one's nonpolar. So all you have to do is determine which is which. And you may not even have to do a measurement. You might just have to do a solubility compatibility test. You know, try to dissolve this compound in a polar solvent. If it won't go, but it will go in a nonpolar solvent, then you got your answer. And you don't have to spend a lot of money on equipment that's required to measure the polarity of the molecule. Assuming this is well, even if it is a gas, you can put it in solution. Okay, so that's the description here. These slides are saying just what I said. Square planar molecular structure fits the data, and it's also theoretically the best, based on the theory. And there you go. It is indeed a nonpolar molecule, has no dipole moment. So the square planar geometry fits the data the best. Okay. That's enough for chapter 8. And I went about 40 minutes over, which is typical for me. Okay, any questions before we call it a day? I'll stop the share.